Hello, everybody. Thank you so much for coming. I'm Mike Beer. I'm a member of the physics faculty here at Southern Miss. I'm very happy to welcome you to the 2018 Grayson H and Jane Dishong Rayborn Lecture in Physics and Astronomy. Dr. and Mrs. Rayborn made this series possible through a generous grant in 2015. Dr. Rayborn has a long history of service to the university. He was professor, chair, associate dean, and director of the School of Mathematical Sciences. He's now professor emeritus. And with the endowment of this lecture, Dr. and Mrs. Rayborn continue to serve the university and the Hattiesburg community, and we all thank them very, very much for that. I'd also like to recognize that our provost, Dr. Stephen Mosier, is here. Thank you very much for joining us. This lecture, this version of the Rayborn Lecture, is offered in conjunction with University Forum. And University Forum is grateful to the Office of the President and the Honors College at Southern Miss for their continued support, and are especially pleased to be co-sponsoring the Rayborn Lecture in Physics. I want to let you know about the next forum. Forum presents 6 speakers each year. Please join us on October 23rd when Jose Antonio Vargas, the Pulitzer Prize-winning journalist and immigrant rights activist, will speak at University Forum here in Bennett at 6:30. That's October 23rd. Our speaker today is Dr. David Spergel. He obtained his bachelor's from Princeton and his master's and doctorate from Harvard. He's currently the director of the Center for Computational Astrophysics at the Flatiron Institute and the Charles A. Young Professor of Astronomy at Princeton. He has received numerous awards for his work. A partial list includes the MacArthur Fellowship, the Shaw Prize, the Gruber Prize, the NASA Distinguished Service Award, and recently the Breakthrough Prize in Fundamental Physics. He's a member of both the National Academy of Sciences and the American Academy of Arts and Sciences. He's the author of over 300 scientific papers and has over 100,000 citations. Much of his work involves analysis of the microwave background in space that can be used to investigate the structure of the universe. And his talk today, Our Simple and Strange Universe, will introduce us to some of that work. So please help me welcome Dr. David.
Thank you. Thank you so much. I want to begin by thanking the Rayborns for bringing us here. Thank the physics department and the Society of Physics students for their hospitality today. And thank the university for having me here. What I want to talk to you about today is really what we've learned in cosmology in the past 20 years. And it's been a remarkable journey in that we've discovered that the universe is both remarkably simple and remarkably strange. And the sort of half-full version of the talk, depends how you like to view things, is that a simple model fits lots of the data. The missing part, the strange part, is that we don't understand much of the universe. Atoms, the stuff that makes up us, makes up only about 5% of the universe. The remaining 95% is in the form of what we call dark matter and dark energy. Stuff that, as you'll hear in the talk, we could detect its effects, but we don't know what it is. And then in the latter portion of my talk, I want to turn to some of the things we're trying to do to understand the nature of dark matter and dark energy. So let me begin by talking about this model we have. What does it rest on? It rests on the idea that the same laws of physics are valid throughout space and time. The universe in some ways is as simple as it can be. Its total energy is 0. The geometry that you learned in probably 8th or 9th grade in Euclidean geometry, the sum of the angles of a triangle is 180 degrees, is valid not only in your 8th grade class with Mrs. Smith, but on the scale of the visible universe. Surprisingly, we learned the universe has gone through at least 2 periods of early acceleration that gave rise to the structure we see. And as I'll show as we look at the data, with 5 numbers, we can fit a host of cosmological data. But in order to explain this, I need to begin by teaching you some basic physics. The first thing I want to teach you is special relativity. The key idea in special relativity for the point of view of this talk is light travels at a finite speed. It takes light a few nanoseconds to get from me to you. So you're not seeing me as I am now, but as I was a few nanoseconds ago. I don't change that much in a few nanoseconds, so it's not such a big deal. When we look at the sun, it takes light about 8 minutes to get from the sun to us. So we see the sun as it was 8 minutes ago. Further out you go in space, the further back you go in time, the longer it takes to communicate. For those of you who saw the movie The Martian, which I recommend very much, it really captures a lot about how we might explore Mars someday, besides being a really entertaining and well done story, conveys this very nicely. If you've seen that movie, it takes 30 minutes to get the message to Mars, and then 30 minutes to hear the answer. And there's a great scene where they sit and they're waiting for that hour to get that signal back. The further out you go in space, the further back you go in time. If you were on a planet orbiting the nearest star, which is about 4 light years away, you would see us as we were 4 years ago. If you were further out, say 20 light years away, someone looking at Earth right now that was 20 light years away would see us as we were 20 years ago. I'd have a full head of hair. Some of you might not be here. The further out we go in space, you go even further back in time. The nearest galaxy is about 1 million light years away. If you were on a planet in an Andromeda galaxy observing Earth, you would see us as we were 1 million years ago. What we'll talk about today is mostly the microwave background. That will be light that's traveling to us for 13.8 billion years. Light that's last interacted with matter only 400,000 years after the Big Bang. So we'll be looking back in time, really seeing in some ways the universe's baby picture, and we will use that to learn about what's going on. So everyone's good with special relativity? Good. All right. Next, we'll move on to general relativity. General relativity, as my academic great-grandfather, Johnny Wheeler, taught. My academic grandfather, Kip Thorne, won the Nobel Prize last year. By the way, they just announced the Nobel Prize today in atomic physics, laser physics. Taught general relativity consists of 2 ideas. Matter tells space how to curve, and the curvature of space tells matter and light how to move. So if we're looking at light traveling from the sun, looking at the sun curves space around it, the Earth curves space around it. So if I'm looking at light from a star at position A, that light travels around the sun, it gets bent, and instead of observing the star at position A, I see it at position B. And this is something Einstein predicted when he developed this theory in 1917. And what made Einstein famous was in the 1919 eclipse expedition, the astronomers were able to observe stars, and as the New York Times reported, lights all askew in heavens. Men of science, was mostly men back then, more or less agog over results of eclipse observation. Einstein theory triumphs. And in a bit of fake news, it says not where stars seem to be or were calculated to be. But actually, Einstein did calculate where it was, and Einstein got it right. But no one need worry. And this was Einstein's great triumph. And over the subsequent 100 years, we have tested this strange theory of general relativity in many ways. most recently through the detection of gravitational waves. And as far as we can tell, general relativity seems to be describing the universe on the largest scale remarkably well. Once we accept general relativity, we end up with a very strange universe. And our concept of space and time have to be changed. Most of us think about space and time as something absolute. General relativity teaches us that all that matters is the relative distance. And I describe things by talking about relative distances. So if I told you that I can travel from New York to San Francisco to Tokyo to London, all going in the same direction, and then back to New York, that tells you that the Earth is round. So by specifying distances, I can specify the nature of space and time. When we apply general relativity to our universe, and the assumption that Einstein made, which is now tested, is that our universe on large scales is homogeneous, we discover that the universe must either be expanding or contracting. And what Hubble showed is that it's expanding. We live in an expanding universe. Now, I think for many of us, this is actually the conceptually hardest idea in the talk, because we think of space as absolute. Now, the picture that I have of expanding space is I suppress one dimension. I imagine we live in a two-dimensional universe. And all of us are living on the surface of a sphere. And each galaxy is a different dot on the surface of the sphere. The radius of that sphere is time. So as the universe ages, the sphere gets bigger and bigger and bigger. And that's the picture to have. As we progress in time, the galaxies get further and further apart as the universe continues to expand. As this happens, you can see our universe is getting less and less dense with time. As it's expanding, light itself stretches. As a result, the universe gets colder and colder with time. One observational consequence of this is distant galaxies. As we look back in time, remember, looking out in space, we're looking back in time. Distant galaxies appear red because the light from that galaxy, as it moves towards us, gets stretched, and blue light gets stretched into red light. This sort of in some ways surprising picture, but one that we've now had for almost 100 years, has some important implications. If this is going forward in time, we're now going back in time this way. As I go back in time, the early universe, and that's what we see, remember, looking out in space, is denser and hotter. And the further back I go, the denser and hotter it gets. Eventually, if I'm contracting this balloon that we live on, our universe, it collapses down to a point. Not a point in space. The Big Bang didn't happen at a place. The Big Bang happened everywhere, but it happened at a moment in time. That moment in time we call the initial singularity. One of the questions I always get when I talk about cosmology is what was there before the Big Bang? How did it start? The answer is we don't know. Our knowledge of physics breaks down at those high curvatures and high densities. We don't know how to go through the singularity. This is an area of very active research. I'm happy to say a little bit about it, but in the end, I can really only talk about speculation. What I will focus on is not the moment of the Big Bang, but most of my talk will focus on about 400,000 years after the Big Bang, the point at which the temperature of the universe drops to 3,000 degrees. Electrons and protons first combine to make hydrogen, because that's the moment that we observe, and that's what we'll use to learn a lot about the universe's history. Right, here's another vision of that quick history. We start out with the Big Bang. There's this early moment of expansion. We think that most of the deuterium and helium in the universe formed in the first 3 minutes of its history. We have some nice tests of that. About 300 to 400,000 years after the Big Bang, atoms form. And when we look out in space, and the pictures I show you of the microwave sky, we'll be looking back to that early moment. This microwave background radiation, that will be the theme of much of my talk, is the leftover heat from the Big Bang. It's something that fills all space. It was first detected by Penzias and Wilson at Bell Labs when they pointed their microwave background antenna in all different directions and looked around and saw this leftover radiation. Those of you who've looked at television with instead of using a cable, we're using a TV antenna, you have seen some of the microwave background. When you turn your TV between channels and saw static, about 1% of that static is microwave background radiation. So what we do is basically a more sophisticated version of your TV antenna. We'd like to pick up more than 1%. Your TV antenna is pointing in all directions, mostly picking up emission from the ground. So what we'll do is either go to a very isolated spot, and I'll show you some pictures from Chile, and we build a radio telescope and we point it up to the sky and try to get away from all the Earth's emission. Or better yet, and I'll show you some results from satellites, we send satellites out to 4 times the distance of the moon, far away from the Earth's radiation, look deep out in space, and look at this leftover radiation and map it. And this is the first time we did this. This is the COBE satellite, which launched in about 1989, reported its results in 1990, and the COBE team leadership won the Nobel Prize in 2006 for this work. They were able to see not only this nearly uniform radiation at a temperature of about 3 degrees, 2.728 to be precise. What they were able to detect, and that's shown in this picture below, and this shows the whole sky, are tiny variations in temperature from place to place, variations of that picture about 18 millionths of a degree. This red thing here, which you'll see in a bunch of pictures, this is showing the whole sky, is our own galaxy, the Milky Way. From the point of view of a cosmologist, this is just foreground dust smudge. The Milky Way, our own galaxy, that stuff is only like 10,000 light years away. It's really nearby. It's stuff that's only been traveling to us for 10,000 years. It's like looking out your car window at this beautiful scene in the distance, and there's some smeared out dead bugs on your window screen. That's how we cosmologists think of galactic astronomy. Don't tell my colleague Bruce Drain, who's devoted his life to studying that galactic dust that. So what we wanted to do, and for the first part of the talk that I'll turn to in terms of some results, is we want to study this in more detail. And the next step beyond COBE, and this was something that I was part of, was NASA had a competition, asked us to submit proposals on what the next satellite to build would be. This is now back in about 1996. We and 45 other groups submitted proposals. NASA selected ours, and we built what we initially called the microwave anisotropy probe. Dave Wilkinson, who was part of COBE and was a key part of our team, sadly died of cancer the year before we reported our first results, and NASA let us name the mission after him. So we will refer to this as the Wilkinson microwave anisotropy probe. And here's a picture of our satellite. It went out about 4 times the distance of the moon to what's called the L2 point, and went out and made this map of the microwave sky. And these are the maps we made. It's higher resolution than that COBE picture. Again, you see the galaxy across the center. This picture is at different frequencies. Here's 5 different frequencies. As we go up in frequency, the galactic emission gets dimmer and dimmer. And what we are interested in actually is getting rid of the galaxy by using the multi-frequency data to project it out and make what I think of as the universe's baby picture. This is what the best we can do to remove the galactic emission and make a picture of what the universe looked like 13.8 billion years ago as we look out to the microwave background. Again, you're looking at the whole sky around us, just like you're looking at a picture of a globe. And this variation in color reflects variation in temperature from place to place. In this picture, the red regions are about a 1/10,000th of a degree hotter than the blue regions and represent regions that are slightly denser than the blue regions. At the time we made this map, now almost 15 years ago, it was a technical accomplishment to measure things at the millionth of a degree level. Now we're pushing towards a few billionths of a degree level. So when you look at this picture, one of the things that should stick out is the letters SH. I don't think this is a cosmic message, honoring Stephen Hawking. I think what this is telling us is about evolution. Let's consider 2 groups of humans. One set of humans are very calm. They see tigers in the woods. They know it's not tigers, it's just some wind blowing. They're usually right. There's a second group. They're very jumpy and nervous. Every time they see any pattern, they assume it's there. 1 time out of 10, they're right. Those people are eaten. These guys are our ancestors. So we're a little jumpy, a little nervous. We often see patterns when they're not statistically significant. This is why I would ignore that SH as a cosmological signal, because we're good at finding things like that. Instead, we're going to do statistics on the map. And the statistic that I'm going to keep using, because it really describes very accurately what's going on, is what is the amplitude of temperature fluctuations as a function of scale. So what I'm going to do, what we do in our analysis, is we throw down circles. We get the average temperature in that circle, and I move that circle around. And I look at what is the temperature fluctuations as a function of the size of that circle. And that I think, yeah, and I'll show those plots. And what those plots are showing is how sound waves behave in the early universe. We see a pattern of sound waves, and I'll just skip actually here to the data. And this shows how lumpy the universe is as a function of scale, what the amplitude of those temperature fluctuations. So I've basically just taken that picture you saw and converted it to a graph of what the temperature fluctuations are as a function of angle. And you can see there's a characteristic angle that corresponds to about a degree. That's the average size of that hot and cold spot. What's plotted here as the points are the measurements that we took. In this particular plot, and I'll show a few others like this, the black points are the ones that we took from space. The other color points are ones taken from ground-based experiments that are better at making measurements on small scales. Smaller angles will be on this plot, larger numbers. And what's remarkable is that curve that goes through all that data as it goes up and down. And that curve is our model with the basic parameters of our cosmology and an age of the universe, a composition, and the properties of the fluctuations. And we can fit this data with just 5 basic numbers in our model. And those numbers are the age of the universe, the density of atoms, the density of matter, how lumpy the universe is, and how that lumpiness varies with scale. And what to me is remarkable is we can take that picture of the early universe, fit the data, and then, as I'll show, run it forward in time and fit everything else in cosmology. So once we've done those microwave background data measurements, all the data sort of basically fits together. We do computer simulations of starting with those early conditions 400,000 years after the Big Bang, how we can run it forward in time and really just with gravity predict the statistical properties of the galaxies. And, let's go back to this plot. This shows in these different curves, the red curve is the relevant one, how lumpy galaxies are today versus scale. The points are the data. The curve represents a model fit only to the microwave background. So I can look at the universe then, run it forward to today, and fit all the statistical properties of the galaxies. And if I were to give this talk about 8 years ago, I would stop here and say we have a model, and the model fits all the data, and here are the basic components of the model. General relativity describes the universe on large scales, a universe made up of atoms being 5%, dark matter being 25%, and this dark energy associated with empty space being about 70%, and a universe with tiny ripples that had roughly the same amplitude on all scales. Now, we've got a model. What do you want to do in science? Next thing you want to do is test it better. And the next step in this was the European Space Agency launched the next generation satellite, a satellite called Planck. While it was European-led, much of the key technology was contributed by scientists in the US, particularly at Jet Propulsion Lab out in California. And it made an even higher resolution map of the sky. So while we mapped it 10 years earlier at 5 frequencies, they made maps at 9 frequencies and even higher angular resolution. And here's that same plot showing first the curve with our theoretical model. We had measured the data in blue that went up to here. I'll stop hitting myself and knocking that off. Then from the ground in 2013, and I'll show some more results from our experiment in Chile, we measured the green points. Our colleagues in University of Chicago measured the red points. And then the Planck satellite measured those the open circles. What you should take away from the plot is 2 things. First, this is, at the experimental level, really reassuring. We have 4 different groups looking at this leftover heat from the Big Bang, making measurements, all reaching the same conclusion on what they see. These are hard experiments to do. This is why we do them independently. This is why we try to check and make sure we get the same answer. So first, we've got consistent observational data. And then we have our theoretical model. And remember, that theoretical model was fit. The first plot I showed you just showed 3 wiggles. And now it's successfully, without changing parameters, fits even more data. And the data has continued to improve. These results are from the Planck experiment with results that came out it was submitted to the journal about 3 months ago. I'm the reviewer on this paper. I wrote the report on the flight here. So it's going to appear, I believe, in about a couple weeks. I have a few suggestions for improvement. This shows first their temperature measurements, then next the measurements of temperature and what we call polarization. Light is polarized, that's why you wear polarized glasses. That reflected light consists of electromagnetic waves, and it can propagate towards you with either electric field pointing this way or this way. Those are different polarizations. And we can measure the pattern not just in temperature, which is the top plot, what I showed you earlier, but the patterns in temperature and polarization, and even see how light is deflected by gravity. So I don't want to go into the details of these plots, but to say there are 4 independent measurements, including the temperature measurements, all fit with the same model. And the impression you should take away from this is we've made very precise measurements, and the same simple models now fitting all of this data. And what we are struggling with right now is trying to see, as our data continues to improve, do all the pieces really fit together? And this is where my talk will get a little ambiguous, because right now we're a little confused about where we are. So some pieces fit together very well. So this shows how we can measure the distance to galaxy clusters as we look out in space. So this is data showing, as a function of, as we look out in time, look at redder and redder light. Each point on this graph is a different experiment showing the distance measured from those observations of galaxies compared to the distance we infer from the microwave background. And the point here is the data basically all fits that line around 1. It all sort of agrees. But this is the one, and this is from this paper that recently came out, measuring the expansion rate of the universe. This is what we call the Hubble constant. And the gray curve is what happens if we take what we saw 13.8 billion years ago and we extrapolate forward to today. And we're plotting the expansion rate of the universe on the y-axis against how far back we go in time, what we call the redshift. That's how red the light is. So this is the universe about 8 billion years ago here, and measurements that we take looking at quasars. That's pretty good, a little off, but but within it, you expect some points to be a little bit off. These are measurements that were just released with another quasar sample. These are measurements with galaxy sample. And if I'm up to here, it looks like I'm doing really pretty well. That we've been able to extrapolate from 13.8 billion years ago to pretty recently and get a consistent picture. What many cosmologists are debating about right now is trying to understand what's going on today. This is the universe today. The model predicts that the expansion rate of the universe should be, in the appropriate units, about 68 kilometers per second per megaparsec of the universe. We'll just think about it as 68. But measurements with the Hubble telescope, led by Adam Rees, who won the Nobel Prize for the work he did in 2011, should get a measurement of 73. Now, 68 and 73 are pretty close to each other. When I was a graduate student, people were trying to measure the expansion rate of the universe, and they couldn't agree whether it was 50 or 100. And it was just hard to get these things accurate at all. And when people describing the properties of the whole universe agreed to sort of, about 10%, that's not bad. But we think we've gotten pretty small error bars on the data. And if there's both results are right, that says there's something wrong with our basic model. One of the most disturbing possibilities, and something that you'd be tempted to do looking at this data, is to take that gray curve and say, what do I have to do to my cosmological model to make it bend up and go through the points? It's pretty close. What you have to do is make the universe's rate of acceleration, which is what you're seeing, that going up is accelerating, get faster with time. That would, if correct, that would imply that the universe is being, that the dark energy that makes up the universe is growing in strength, that the universe is accelerating ever faster. That's a very scary universe, because if the universe starts accelerating faster and faster, it's a runaway process, and eventually you will tear apart every galaxy in the universe as space gets stretched faster and faster. Worse yet, soon after that, you'll start tearing apart every star in the universe. Then you'll start tearing apart every single atom in the universe. And eventually, and pretty quickly afterwards, the fabric of space-time gets torn apart in what we call a big rip. And if we just extrapolate to the future, the whole universe is destroyed. That's not a good outcome. Don't panic yet. Probably, well, if it were to happen, it's going to happen many billions of years in the future. I hate to break it to you, you'll all be dead a few billion years in the future, no matter what advances we have in healthcare. Second, there's probably something wrong with the data. And even if there isn't, we may not yet have the right model, but it shows you that the stakes are high here in some sense. Then let me turn to something we just reported that suggests additional problems, that give you just a sense also of what we do when we make our measurements. This is a paper that we, as you can see, we just submitted to the journal a few days ago. This is a team of people, and I want to list the names of the team just to get a sense of how international our science, our efforts are. This is work done at the Subaru Observatory in Hawaii. It's a telescope in Hawaii built by the Japanese with a camera built in Tokyo. The software and the analysis is mostly led out of a group at the US, principally at Princeton. There are collaborators all over the world, in California, in Boston, in Switzerland, in France, and we all work together. Very hard to find a time we could all talk on the phone together, spread out that way, but we somehow managed. It's why I'm often on the phone at 11 at night as we discuss the paper. And this is what we reported on our measurement of the amplitude of fluctuations. And I don't want to get into the details here, but the gray band is what we measured. The points, the last point on the bottom is what comes from the Planck satellite. And, you know, things don't, they're close, but they don't quite line up. So what we're trying to figure out right now, what's sort of driving us in the field, is figuring out what's wrong. And there's fundamentally three possibilities. There's something wrong in the measurements that the Planck satellite made of the fluctuations in the universe. There's some calibration errors. There's something in their detectors that's making us small. These are hard measurements, 1% error. We haven't figured out what that is, but it could be there. The second possibility is the measurements with the Hubble telescope have something wrong with them. There's systematics in that data. Another possibility is we're just not getting the errors right. These numbers are close and we just haven't done our analysis properly. What would be the most exciting possibility is there's news physics, that we're seeing that the universe is going to be torn apart in a big rip. Our general relativity is failing on large scales. There's something really important to be discovered here. So what do we do next? We need to get more data. We need to look at this in other ways and make progress on this, and this is what we're trying to do. So one of the things we're doing is we're building new telescopes in Chile. I'll show you some data that we're taking from a telescope we're operating now that we call the Atacama Cosmology Telescope. It's up in the Atacama Desert. This is a map of Chile. It's up at about 17,000 feet. So you're at a place that's really high and dry, much drier than here. This would not be a good place to do microwave background experiment measurements. You want places with low humidity. New Jersey is also not a very good place either for that. So we go up in the high desert where it's really dry, and we build this telescope shown here, and you can see we build a ground shield, and we have all sorts of things to protect it from emission from the ground. So we're mostly looking at the microwave sky. Again, when we put this together, we've got collaborators really from all over the world, mostly based here in the US, but we have collaborators in Chile, we have collaborators in South Africa at the University of KwaZulu-Natal, in Canada, in the Netherlands. It really is an international effort. Here's some of the people in the collaboration. And many of these people, I mean, when working on an experiment like this, you become, more than just collaborators. You really become friends, and you sort of, some of the people here, we've been working together for about 15 years. Others you can see come in as students and then stay with the collaboration over time. And what we're doing now is we're re-observing some of the regions seen by Planck. Here's a piece of the Planck map. We're going back at higher resolution and higher sensitivity to test that. And what we are doing in the analysis is when we analyze this data, we're going to do something we call blind analysis. We don't want to be biased in our analysis by our assumptions. There's a problem I think we actually all have to be very conscious of when we look at whether it's data or the newspaper. We all have certain assumptions that come in. We all have certain results that we want to, expect when we look at the data. To get very contemporary, if you watch the discussion in the Supreme Court hearings, without your view of what goes on ends up being biased by what assumptions you had going in. You just listen to people. How they interpret that is based on their ongoing assumptions. And we want to avoid that as scientists. So what we do when we analyze our data is, we want to measure things like that expansion rate. We don't want to be biased by what we think the answer is. So we don't want to make any assumptions or analysis that will be consciously or unconsciously affected by our notion. So we come up with a blind analysis plan. We make a list of all these things we do to test that the data is correct before we look at the implications of our tests. We don't work through to the answer, but do it step by step. This is our analysis group, and the point is not so much the pictures of us, but though that's a nice group, but what's on the blackboard behind, which is we write down this long list of all the tests we want to go through, particularly tests that are what we call null tests, where we take the data, say, measured on Monday, and the data measured on Tuesday, and we take the difference between it, and that should be 0, because the universe doesn't change from Monday into Tuesday, and we make sure that its statistical properties behave the way that they ought to check our model of what's going on. And then, what we're doing now is we're working through this analysis. I don't have results to show. I don't actually know what the answer is at all because the analysis is blind. But what we hope to be able to say from the work we're doing now is, do we agree with the Planck experiment? Are we finding their value for the expansion rate? Or do we agree with these measurements from the Hubble telescope? And, that would suggest there might be something wrong with the Planck measurements. So what's exciting to me about being a scientist is I don't know what the answer is, but we're going to find out. And that's why that big group of people comes together to do that. So that's one thing we're doing right now to look towards finding the answer. Another thing we're trying to do is try to understand the nature of dark energy. We want to get more points and more accurate points on that curve showing how the universe's expansion rate varies with time. And to do that, we want to do this in a way that's very clean. And when you observe stuff from the Earth, you have to look through the atmosphere, and that makes the observations more difficult to interpret. So what we want to do is go back to space and launch a satellite to study the nature of dark energy. And the big project I'm working on now, one that we hope to launch in 2025, is a NASA mission called WFIRST. And this mission actually has an interesting history. Every decade, the astronomy community gets together and says, what's the most important thing we should build? When we did this 4 decades ago, we decided that would be the Hubble telescope. And we got together and 15 years later launched the Hubble telescope. And every decade we identify the most important priorities. And the top priority that we identified was building a wide field infrared telescope that would map the sky and study dark energy, and also use it to study the nature of exoplanets. So we made this recommendation in 2010 as the next big thing to do. Unbeknownst to us, the National Reconnaissance Organization, that's the spy satellite agency, they're the ones that build telescopes that are pointing down. They have built 15 telescopes that they have launched that are the size of Hubble, that have been pointing down. Because of a program that got canceled, they actually had 2 telescopes that hadn't been launched yet that were sitting in Rochester. And because the program was canceled, they were thinking of destroying it. One of the craziest phone calls I got was from the head of NASA Science about 6 years ago that said, we just learned there's a leftover telescope sitting in Rochester that seems like a pretty good match to what the astronomy community wants. Do you think we should use it? I need to put together a small study group to look at its possibilities. You know, I joke it's like going to a back alley in a bad neighborhood and someone pulls up with a truck and says, I just got this really great television. Don't ask where it came from. It doesn't have directions, and don't ask too many questions, but it's a great deal. And that's sort of what it's been like initially working with this telescope. It was a beautifully defined telescope, but because it came from the classified side, I have no clearance, we can't ask too many questions. But it turns out to be a very good match to what we want. And what we've been doing is working to design the instruments for it. Actually, this is actually an old slide in that it's a fake picture of the telescope because the telescope image was, it wasn't classified, but it was called ITAR sensitive. ITAR is a set of rules that says these are secrets. They could only be shared among the 300 million of us that are US citizens or green card holders. And without checking to see that everyone in the audience is either a US citizen or green card holder, I couldn't show a picture of what the telescope looked like. I must admit, I always found this to be one of the more bizarre types of classifications, because most secret that could only be shared among the 300 million of us is not that deep a secret. But anyway, we want to put 2 instruments on this, a wide field instrument that will let us image the sky. This telescope has the resolution, the sensitivity of Hubble, but with this camera, every picture we take will be 100 times bigger than every Hubble image you've seen. So imagine every Hubble map picture you've seen. Now, every time you point the camera, it's 100 times bigger. So we get an enormous amount of data. We'll be able to map almost the entire sky at Hubble resolution. And that will let us look at large numbers of supernova explosions, images of galaxies, map dark matter. We're also putting a coronagraph on the instrument, telescope, that will let us image, and we hope get spectra of planets around nearby stars. We'll put 2 instruments on this. And so the basic picture to think about this is a telescope. It's Hubble times 100 in terms of the images. And we've learned a lot from Hubble. It's going to be a terrific telescope for studying dark energy. We can use this to look at supernova. We can use this to map the distribution of large-scale structure. We can use this to look at the large-scale distribution of matter. We'll redo that expansion plot that I showed earlier with high precision. Not only that, we'll be able to study planets around nearby stars through lensing. We'll be able to detect, we think of order 3,000 planets, including many smaller than Earth, through their gravitational effects. That's just another piece of astronomy. We'll be able to use this to look for exoplanets. I'm speeding up because I'm running a little late. So we've been working on this. The most recent developments in this, and this has been actually a bipartisan experience for us. We managed to be canceled by the Obama administration and then restored by Congress. This year we were canceled by the Trump administration and restored by Congress. So I've got to learn all about politics, a little bit at least, go down to Washington, testify in front of Senate authorization committees and things like that. But I think we're in the House and Senate bill for 2019 at the moment. The House and Senate have come together and passed a bunch of bills for the budget. They've not passed the NASA budget yet. I'm hopeful. We're trying to stay alive. But we've actually been fortunate when we've gone to Washington to get bipartisan support in making this happen. And since you've got a senator on the authorization committee, put a good word, appropriations committee, put a good word in for us. Let me conclude. What did I want you to take away from this talk? A couple things. The first is, at a basic level, we have a really simple model that starts with general relativity, describes the universe starting from the Big Bang, that seems to fit a lot of data. There's some tensions. Those points might be a little bit off, but broadly seems to fit. And while that model's simple, in many ways very strange. It says atoms make up only 5% of the universe. We've determined the universe's composition, its basic parameters to high precision. But we are seeing in the model some interesting anomalies. We don't know yet whether these anomalies are pointing to brand new physics, whether we should need to move beyond general relativity, whether things are even stranger than we thought with dark matter and dark energy, or whether these anomalies are just the errors you make when you do precise experiments. So we need to go out and do things more accurately. It's a situation where I don't know the answer. But these questions, to me, I think are profound and exciting. And this is what we do as scientists, as we go out and try to figure out what's going on. And it's a story that continues to unfold. So let me stop there and take some questions. Thank you.
Hi, thank you so much for speaking. My question for you is, how will the James Webb Space Telescope affect your research?
So the James Webb Space Telescope, which is a telescope that is going to have about 6 times the collecting area of Hubble and look in the infrared. It will let us look back in time. So as I mentioned, when we look out in space, things get redder the further out we look, because light redshifts. So if we want to study the universe, say 10, 12 billion years ago, so that's remember the universe about 13.8 billion years since the Big Bang, look at early galaxies and galaxy formation, we need to observe in the infrared. And James Webb Telescope does that. So it's going to be able to tell us not so much about the universe's first moments that we're doing in the microwave, but sort of the first billion to 2 billion years. And we'll be able to trace the evolution of galaxies. It's also going to be able to tell us about the atmospheres of stars through what we call transit spectroscopy. We're going to look at, atmosphere of planets. We'll look at planets that pass in front of stars, and we'll be able to observe their atmosphere that way. So those are two of the big things I'm hoping we'll learn from James Webb. James Webb will also tell us more about the properties of stars like supernova, which will let us more effectively use them to study distant galaxies. James Webb is actually quite complementary to this WFIRST telescope I'm talking about. WFIRST is a survey telescope. It basically looks at lots of the universe, doesn't study it in great detail. In some ways, I think of what we do in science with most of what we observe falls into two approaches. Either you get a big sample, you do big data, and you learn a little about lots of different individuals, or you study individuals in great detail. WFIRST is doing the survey. James Webb is studying individuals in detail. Great.
Hi, I enjoyed your talk. So I have two questions. My first question is, can we observe the effects of dark matter and energy on smaller scales, for instance, large-scale biological evolution? And can this model be applicable to trends in evolution here on Earth?
So dark energy doesn't seem to interact very much at all with ordinary matter. We can only observe its effects on cosmological scale. Dark matter, on the other hand, which seems to be some type of new subatomic particle, might be potentially observable in the laboratory. So people are doing underground experiments where you try to get away from all the background and wait to see a dark matter particle come in and strike an atom and make it move. Now, dark matter, if its properties are like what our current best guess is, and we don't know what it is, but we have ideas, then dark matter actually, I think it works out that basically once in your lifetime, a dark matter particle will strike an atom and make it move in your body. So it doesn't interact much, but it does interact a little bit. It interacts in terms of biological evolution much less than protons do, cosmic ray protons and radioactivity. We think most of the ways in which, say, background radiation or background particles from our galaxy affect us is cosmic rays come in, they strike nuclei in our bodies, and they produce mutation. And that's been one of the drivers of evolution, is radioactivity that's both cosmological coming in from our galaxy and radioactivity from radiation on Earth, from radioactive decays. Both play a role in creating mutation, as does this transcription error in the biology. So all those things sort of add up to the mutations that both have the detrimental effect of leading to things like cancer, but also the beneficial effects of driving evolution. Compared to those other sources, cosmic rays, radioactivity, transcription error, dark matter is not important at all. It's really relatively inconsequential. So I think both dark matter and dark energy are things that we'd like to understand because it's much of the universe, but their effects on our daily life are at most very subtle. In a sense, otherwise we'd know what that is. If it was interacting with us a lot, we would have figured it out. Right. So the question was, when we think about things like as you go from prokaryotes to eukaryotes, does dark matter play a role? Well, since we don't know what dark matter is, in some ways I'm not 100% confident the answer, but of the stuff that we understand, the answer would probably be no. My current understanding, this is how you go from prokaryotes to eukaryotes, is there was a one-time event when an archaea came along and went to eat a prokaryote and didn't succeed, and eukaryotes all seem to descend from a single ancestor. Yeah.
I had a question. I really enjoyed everything you spoke about tonight. There was a movie that came out, I think, in 1997 called Contact.
Yeah.
With Matthew McConaughey and Jodie Foster. And at the beginning scene, you're kind of going out into space, and it's radio waves. So it goes back in time. I think it started with like the music of the time, and it ended with static, which was at the very beginning when, before radio was invented. And you were talking at the beginning about how light, we were standing a light year away, it would be like looking back at 4 years, or I think it was 20. We'll be looking back at like 10 years away. Does the same thing happen to sound? Does that correlate?
So sound travels at a finite speed, just like light. So this is something, if you pay attention carefully at a football stadium, you'll actually observe this effect, that the sound from the other side of the stadium takes, a half a second to cross the stadium. So when people when people are doing chants together, the people near you are all sound like they're all talking at the same, chanting at the same time. The people at the other side of the stadium are actually a little bit out of phase because it takes sound a bit of time to get there. You're also seeing this effect with thunder, right? We all know you see lightning and then you hear thunder. And that's because it takes sound, which moves much slower than light, sometimes a second or two to get there. And, the trick I think a lot of us learned as kids is you could figure out how far away the lightning is by listening. So light does travel at a finite speed, but it's pretty fast. So light gets there quickly, sound takes longer, and that's how you can figure out how far away lightning is, by that delay between lightning and thunder. And you're seeing, in that case, the finite speed of sound, which is much slower than the finite speed of light. To see the finite speed of light effects, you mostly need to get to astronomical scale. Though if there's some experts in the internet, the fact that it takes a finite time for a signal to get from, say, here to California and back, means that if you're running network computing on the cloud, you'd actually rather run on machines that are fairly close to each other, because the communication delay between the computers start to become significant. A little bit of computer science for you.
Hi, thanks for coming tonight. Would you say that it's probable that the universe will eventually be ended in a heat death? And how does that compare to the universe being ripped, like you were talking about a while ago? And also, how does string theory fall into your research and what you study?
Okay, so this is something where I have to start with a Robert Frost poem, which I'm going to mess up because I don't remember it properly, which is, some say the world will end in fire, others say in ice. I think I know enough of desire to say that I think it'll end in fire, but I know enough of hate to know that ice will suffice. So this is an old Frost poem that sort of gives the two options of a universe that collapses back. We've talked about the universe expanding. Think about that expanding sphere. Imagine that expansion turning around and starting to collapse. Remember, as it got bigger, it got colder. As it got smaller, it got hotter and hotter. In that case, the universe would collapse back down to a point, incredible heat, and the universe would end in fire. And that's one of Robert Frost's options. It's also one of the options available in general relativity. We don't think that option will happen based on the current data. The current data suggests that the universe is expanding and expanding ever faster, getting colder and colder, emptier and emptier. So we think that the future of the universe is for it to get colder and emptier. If the universe is accelerating ever faster, that rate of getting colder gets faster and faster. My bet is it'll turn out there's something wrong with the errors on that data, and it'll all turn out to be consistent with a constant rate of acceleration. That then still gives us a fate that the universe gets colder and colder. When I think about that fate, I'm heartened by an idea by my colleague Freeman Dyson, who says, what we really care about is in the future, remember this is future billion years away, that we have intelligent thoughts, that as long as we can get more efficient with time, so that we can, the amount of energy it takes to have a thought keeps going down faster than the universe expands, there's a possibility of life and intelligence going on forever in such a universe. None of this is under our control, but it's fun to think about. Oh, and then string theory. So string theory, so one of the things I thought I'd get a question on, I bet I still will, is to go back to what was there before the Big Bang. What happens when we extrapolate through that moment of singularity? Well, what happens when we try to extrapolate the physics is we run into the fact that we've got these two great ideas of 20th century physics, what I view as two of the great intellectual accomplishments of humanity in the 20th century, general relativity and quantum mechanics. They both work beautifully. We try to tie them together at very high densities and temperatures. The theory breaks down. I try to do calculations, I get nonsense. We reach what are called mathematical singularities, like that Big Bang singularity. This happens often in physics when we try to get to a point at which the theory breaks down. If I describe the theory of sound waves or how air behaves in this room, treating the air as having a density works very well. Hydrodynamics works very well. But now if I set off an explosion in this room and generate a shock wave, the theory of hydrodynamics tells me that the density of the air in this room has an infinite gradient. It goes from one density instantaneously to another. And the mathematics starts to break down. And that's because treating this room as having a uniform density isn't right. This room is filled with molecules of oxygen and nitrogen. And if I want to have a description that is accurate enough on very small scales, I have to have a theory that knows about molecules. And if you were late 18th century, early 19th century physicist, you would have a theory of the universe, of this room, that would work very well most of the time until you got down to the atomic scale, because you didn't understand atoms and molecules, and you needed new physics to go beyond that. So that's where we are today. When we try to combine quantum mechanics and general relativity, we're getting nonsense. Our theories are breaking down. And that means we can't answer what is going on very close to that initial singularity. String theory is an attempt to unify quantum mechanics and general relativity into a mathematically consistent theory. And the hope is if you have mathematical consistency, that's a guide towards developing the next big step in physics. Some of the smartest people I know have been working on string theory for the last 30 years. They've made a lot of progress in understanding some of the mathematics of the theory, a lot of progress in understanding the consequences, but we're still very far from knowing, is this the right way to go? Is this the theory of the universe? Or have they all been going down a blind alley? This is something a couple of us were talking about over lunch, right? Which is, as a mathematician, you get to imagine all these possible mathematics, and as long as you have a consistent theory, you can have something that you know is correct, because it's valid mathematics. As a physicist, we get to learn pieces of mathematics This piece over here might describe the universe, or it might not. So string theory is certainly elegant mathematics. It could be the guide we need to tell us what's going on in the early universe. We just don't know yet.
Hi again. So I recently, as of 2 weeks ago, accepted a civil service position at NASA Johnson, and
Congratulations.
thank you. Oh, and with that relationship, I'm very curious about your experiences with the NASA Space Advisory Council and your position there and what administration it was under. I have another question, my brother's question, and that is, which instruments are you planning on using to explore the dark energy and dark matter on the W first?
So the first one's easy. That's the wide field camera is what we use to map the universe inside the dark energy. NASA's, I think, a great agency to work for. When you look at surveys of civil servants to rank their job, NASA has always the highest ratings. People like working for NASA. It's the only agency that people on the random people on the street wear your T-shirt. There aren't that many people wearing Department of Transportation T-shirts. So I think one gets to work on really exciting things. But probably most importantly, I think it's the NASA, the people I know who work for NASA are enthusiastic. I know the NASA leadership well. They're excited about what they do. It's probably the least political of all the agencies I've seen in a bunch of different ways. Only the top 7 people in the agency are actually appointed by the president. And even among those, usually only the NASA administrator and the deputy administrator and the congressional liaison. So only those 3 change when the administration changes. Even then, there's often continuity. So there was the same NASA administrator from the Bush administration through the beginning of the Obama administration. So that's doesn't usually, that's different for most agencies. And kind of with, I work more with the Science Mission Directorate than the Human Exploration Directorate because of my work, so I know the people there best. But the people I know there, I have always felt at the top administration level within NASA, wake up in the morning thinking, how do I make NASA work better? Right, so I think that there's just good leadership there. And I think at the individual centers, the center directors, again, are trying to make this agency work. So it's healthy on the top, and it's healthy on the bottom, in that people come in, NASA can attract really good people, and they work hard and they do good stuff. Like any job, your travel forms are awful. It is a government bureaucracy. There are days where there will be unnecessary headaches, but you're fundamentally working with good people, and there's only a few lawyers to deal with. So I think it'll have fun. I think it'll be a great. What will you be doing there? Yeah, so there's a lot of this is working on the next generation spacesuit. So just if people didn't hear, there's a lot of interesting developments in that area. And I think developments coming within NASA, developments coming from particularly some people at MIT. This is an area now, one of the exciting things about aerospace is there's all these new entrants into the field. Companies like SpaceX and Orbital and Blue Origins, and with that, they bring new ideas and new approaches. So I think in some ways, this is one of the most exciting times in space because things are changing at the level of what's happening with developments of rockets, developments of spacecrafts. What's also happening, putting on my sort of NASA Advisory Council hat, and this is something I was just in Vienna this summer at the International Astronomical Union meeting, is there now more entrants there are more countries doing serious stuff in space. So it used to be just the US and the Soviet Union, then Europe and Japan became significant players. Now we're seeing China developing a major space program. India's developing a major space program. In some ways, as Americans, this is the competition, but in other ways, we're all learning from each other. And the fact that there's so many new players coming in and new ideas coming means this will drive the development of space missions more quickly. This will help drive space science more quickly.
I think we have time for a few more questions.
Hello. I had a question on the constant rate of acceleration. In your graph, you had an anomaly of the rate, basically.
Yep.
And I was wondering, because I was looking at it, and the line of best fit through your data didn't exactly hit any of the points. So I was assuming, so if you assume that your data that you collected independently was accurate exactly, could the speed of expansion actually fluctuate, like accelerate and accelerate, rather than just one or the other?
Almost certainly, right? So this is assuming the simplest model in terms of the composition, that the dark energy is constant with time. That's what's behind this curve. So it could be that it's gotten more exotic behavior. But I think it's important to keep in mind with data and errors that the right model doesn't actually go through all the points. So you should read this error bar as there's a 68% chance that the value is between the bottom of the error bar and the top. You can double the size of the error bar, and there's a 95% chance that the point is between the bottom and the top. So I think, except for that blue point, which worries me, all these other points are within the 95% range. And because only 68% of the time you should be in the points, it should be, and it sort of works out, that roughly 1/3 of the points should be off the line. And these yellow points and orange points are the same measurement, really. So there's really 5 measurements, and 2 out of 5 are off the line by about 2 sigma, and that's about what you expect. So if it were only the data from here over, I wouldn't worry. That blue point is about, for those of you used to it, about 3.5 sigma off the line. And if the errors are right, that shouldn't happen. That should happen less than 1% of the time. So that blue point is far enough off that either it's wrong or the gray curve is wrong. And that gray curve could be wrong either because the experiment is wrong or the assumption that the dark energy is constant is wrong. So that's how I read that data.
Thank you for your talk. Sorry. Personally, do you realistically believe we could achieve human long-distance space travel?
Do I think we can achieve human long-distance space travel? Well, it depends somewhat on what we mean by long distance. The next big step is going to Mars. And that's something I think we can do, and if we have the will, we can do it within the next 20 years, certainly. So to get to Mars, we need to do 3 things. We need to build a bigger rocket, and we're working on that. We need to be able to do entry on Mars, land something on Mars that's heavy. We think we know how to do that. It's going to require some technical development. And the other is getting to Mars is you're exposed to a lot of cosmic rays. This actually got to the question I was asked earlier about dark matter and talking about mutation. So that you get a lot of radiation damage. So if you go to Mars, there's a reasonable chance you'll develop cancer from the trip and die of cancer 20 years later. So that's a risk for the astronauts. My hope is we make enough progress on treating cancer that that risk goes down. Or we have to be willing to find, and actually knowing the astronauts, a lot of them would take this risk, people who are willing to accept a significantly higher cancer risk in order to go to Mars. So that's sort of the next big step in SpaceX for human space exploration, is getting humans to Mars. And it's hard. My own view on this is it's something we should do not just as Americans, but like the space station, we should do this as a world community. We should do this working together with Europe and Japan and China and Russia. It's an opportunity for us to do big things as humans, and there are ways to do that in which we don't share our technologies. So that's how I'd like to go to Mars. Now, getting beyond Mars gets hard, because if we start to ask about travel to distance, to near, even to the nearest star, even if we could travel at half the speed of light, it would take 8 years. We don't really have any technology today that looks like it could get us to those speeds and distances. So travel starts to take a very long time. So we probably have to have significant advances, both in the technology of how we build rockets, which are radical big steps, also probably in how we handle our own biology. You know, one of the things from science fiction that people think about is you basically put humans into hibernation, because the journey may take 100 years. And then you've got to get, you know, people to be willing to do that. And, you know, and maybe you do that, I don't know, this starts getting into the realm of science fiction, but it's not nuts to me to think about having some people hibernate. And if you want to, if you knew there was a place you wanted to colonize, take along lots of samples of you know, eggs and populate a planet, right? With a few people in hibernation. I mean, you'd have to, you start doing stuff like that. My guess in terms of timescales is, while we can go to Mars in 20 years, in most people's here's lifetime, going beyond the solar system is beyond our lifetimes. This is something that's 100 years in the future, 500 years in the future. It's not 5,000 years in the future. You know, we can imagine what it could take, even if we don't know how to do it yet. It would be my thought on that.
With that, I'd like to present Dr. Spergel with a small gift as a token of our appreciation. And I hope you'll join me one more time in thanking our speaker.
Thank you. Thanks.